Find an equation of the plane that passes through the three given points. The points are 1, 0, minus 2. Let's call this point 0. Then a second point has coordinates 1, 3, and 2. And then a third point has coordinates 2, 3, and 0. Well, to find an equation of the plane with these 3 points, we should know what an equation of a plane is. In standard form, an equation of a plane is given as a coefficient A times the difference between the x coordinates of 2 points plus a coefficient B times the difference between the y coordinates of 2 points plus a coefficient C times the difference in the z coordinates of 2 points. This is set equal to 0, and we should note that A, B, and C are the components, the x, y, and the z components, respectively, of a vector that is normal to the plane and to any vector or pair of vectors in the plane. And we should note that x, y, and z corresponds to an arbitrary point in the plane. So recall, a plane can be given by 3 points that all lie in the plane. And those 3 points, which we could just qualitatively represent with these points I drew in this diagram, those 3 points must be perpendicular to a vector. Or let me rephrase that. The plane in which those 3 points lie must be perpendicular to some vector. Now, we can create a plane in which those 3 points lie by indicating vectors drawn between 2 different pairs of those points. And our normal vector must be perpendicular to both of those pairs of points. And once we have those 2 vectors, we can determine the normal vector by a mathematical operation that we've recently learned in class. Here's a question for you. If we have 2 vectors from 3 points, let's say the first vector goes from P1 to P0, and the second vector goes from, I said P1 to P0, I meant from P0 to P1. And let's say the second vector goes from P0 to P2. Given those 2 vectors, is there a way we could find a third vector that's perpendicular to those first 2? So again, can we find a vector normal to vectors P0, P1 and P0, P2? If we could find a vector that's normal to those, then we'll be able to determine an equation for our plane. If you said take the cross product between those 2 vectors, you would be exactly right. Let's take a cross product between those 2 vectors to find a normal vector. Because remember, you know that the cross product between 2 vectors is a vector that is orthogonal, perpendicular, normal to the 2 vectors in which you take the cross product of. So if we take the cross product between the vector from point 0 to point 1 and the vector from point 0 to point 2, we will get a vector normal to the plane. Now, if we look at the picture we just drew, and if we apply the right-hand rule, well, based off of this picture up here, notice how that normal vector is pointing up. This would correspond to the cross product between P0 and P2 cross with P0 and P1. This right here corresponds to a normal vector in the opposite direction. And I'll just represent that by a different color, and maybe I'll put double arrows here or something. We'll just do a different color. And this is another normal vector. I'll just signify this as normal vector 2. And this normal vector 2 is given by the vector between P0 and P1 and P0 and P2, taking the cross product of those two. Because remember, the cross product depends on order. If we take the cross product of the first one that I did here, that's going to be different than the cross product of the one that I did there. Equal in magnitude, opposite in direction. So this cross product that I wrote is the cross product that I would have labeled as N2. How do you think I know the relative directions? Well, go ahead and review the right-hand rule. I just applied the right-hand rule for each cross product, and that tells me the direction the normal vector should be. For our example, at least for this qualitative sketch, I don't exactly know really how that normal vector is going to look until I plot some points and until I use the information given in the problem. What I'm doing right now is to just conceptualize this problem. And so to be consistent with my picture, I kind of like normal vectors going up. So I am going to calculate my cross product in this order. And let's recognize that this cross product is equal in magnitude, but opposite in direction of N2. Now, fortunately for us, the problem says find an equation, an, implying that there is more than one equation of a plane that passes through the given points. And from this picture up here, you could see that since there's two different normal vectors we could sketch describing that plane, we have at least two different answers. In fact, there's an infinite number of answers because there's an infinite number of normal vectors and points in the plane. With that said, let's calculate P02 and P02, remember, well, let's go ahead and write down the information we have from up here. Where did that go? Oh, I guess I still have to write it down. Let's write down our points. The point P0, I'm saying, has coordinates 1, 0, minus 2. The point P1 has coordinates 1, 3, 2. The point P2 has coordinates 2, 3, 0. If we calculate the vector from P0 to P1, that is going to be the vector with the components given by the differences in each of their respective coordinates. So this is the difference between the coordinates of point 1 and point 0. The vector that goes between those 2 points is the vector with components 0, 3, and 4. The vector P0 to P2 is given with components based off of the differences in the x, y, and z coordinates of our vectors. So that would be 2 minus 1 for the difference in the x coordinates of points 2 and 0. 3 minus 0 for the differences in the difference in the y coordinates between points 2 and 0. And 0 minus a minus 2 based off of the difference in the z coordinates of points 2 and 0. This means that the vector from point 0 to point 2 is given as 1, 3, 2. To calculate our normal vector, we are going to compute the cross product between vector p0 to p2 and p0 to p1. This cross product, I'm going to use the 5x3 matrix technique to help me calculate the cross product. And in doing this 5x3 matrix technique, remember the columns correspond to the components. So the second row will correspond to the first vector. The first vector is the vector from 0 to 2. So this will be 1, 3, 2, 1, 3. Again, that's for vector p0, p2. And then the third row will be from the components of vector p0 to p1. So that will be 0, 3, 4, 0, 3. And again, that's for the vector from point 0 to point 1. In evaluating this 5x3, we'll go diagonally down and to the right and subtract things that are diagonally down and to the left. This means that for our normal vector, our x component will be the product of 3 times 4, that's the blue diagonal going through I hat, minus the product 2 times 3, that's the red diagonal going through I hat. That's the x component. The y component is the product 2 times 0, being the diagonal to the right going through the y hat, j hat, and that is minus the product 1 times 4. And for the z component, that's 1 times 3 minus 3 times 0. And again, I'm getting these values from the diagonals, in which we learned this technique in another video. This means that the normal component is 12 minus 6 for the x component, 0 minus 4 for the y component, 3 minus 3 for the z component. So our normal vector has components 6, minus 4, and 0. Now that we have found a vector that is normal to a plane, let's write our equation of the plane in standard form. Now, our A, B, and C are given from the components of our normal vector. A equals 6, B is equal to minus 4, C is equal to 0. So look at this. Since C is equal to 0, I know that this term is going to go away. Since that term is going to go away, since there's not going to be a term with any z in it, that means this will be true for all values of z. That means our plane is going to be parallel to the z-axis, or in other words, the z-axis would be parallel to a vector in the plane and normal to a vector perpendicular to a plane. Well, let's pick a point. Now we could pick point 0, but really you could pick any of these points that were given in a problem, because all we need is one point in the plane, and we know each of these points are in our plane. But I'm going to stay consistent with the notation I've been using, so I'm going to use point 0 having the x naught, y naught, and z naught equal to 1, 0, minus 2. So now writing our equation of a plane, we have ax minus x naught, so that is 6x minus 1, plus by minus y naught. Oh, well, b is equal to minus 4, so I'll just write this as minus 4y minus y naught. Y naught is 0, so this is just simply minus 4y. There is no z term since c is equal to 0. This then is equal to 0. Here is our equation of a plane that passes through those 3 points. Let's go ahead and sketch what this plane looks like. So to sketch the plane, let's go ahead and create a coordinate system. And what I'm going to do is I'm just going to copy this to our next page to give me more room. Let's create a XYZ coordinate system. The z-axis is going to be vertical, the y-axis is horizontal, the x-axis is coming towards us. Let's choose a convenient scaling and try and be consistent with our scaling. So this will be 1, that'll be minus 1. This will be 1, that'll be minus 1, and this will be 1. Okay, let's plot this plane. Since I know that, since I have 2 coordinates that are left over, the x and y, I know that this plane is not going to pass through the z-axis. There is not going to be a z-intercept, but a line normal to the plane will be perpendicular also to the z-axis. So I'm only going to look at the x and the y-intercepts. So for the x-intercept, we know that we could set y equal to 0. That means we have 6x minus 1 is equal to 0. Or when we solve this, we get x is equal to 1. That is right here in our graph. Let's find our y-intercept. Our y-intercept is found by setting x equal to 0. So when we set x equals to 0, we get 6, 0 minus 1, minus 4y is equal to 0. Minus 4y is equal to 6, or y is equal to minus 3 halves. Minus 3 halves would put us about right here. And so we could construct a plane now, and that plane, notice, is parallel to the z-axis. It doesn't have a z-intercept as we anticipated. And so the equation of the plane that we found is given by this equation up here.